Anti-de Sitter space hypothesis: imagine a universe that curves inward like the inside of a bowl, where space doesn't stretch endlessly outward, but instead bends back on itself. This is anti-de Sitter space, or ADS, a strange and mind-bending model of the cosmos that exists not as our reality, but as a mathematical sandbox, a theoretical playground for some of the most profound ideas in modern physics. In an anti-de Sitter universe, the rules of geometry shift. Rather than being flat or positively curved like our own expanding universe, ADS space has negative curvature. This may sound abstract, but the consequences are staggering. In this kind of space, if you fire a beam of light, it doesn't travel infinitely in a straight line, it arcs and curves, eventually returning to where it started. It's a closed system, one where nothing truly escapes, and everything is subtly connected to everything else. Time and space wrap around themselves in a cosmic feedback loop. Why would physicists care about such a weird, unreal place? Because ADS space turns out to be the key to understanding one of the biggest breakthroughs in theoretical physics, the ADS/CFT correspondence. This idea, proposed by Juan Meldacena in the late 1990s, links two seemingly unrelated worlds, gravity and quantum field theory. According to the ADS/CFT conjecture, a universe with gravity, like one inside anti-de Sitter space, can be completely described by a quantum theory that exists on its boundary, where there's no gravity at all. It's as if all the 3D action happening in the bulk of space is secretly just a projection of a 2D code written on the edge of that space. This is more than just abstract math, it hints that our own universe might be holographic. That what we perceive as depth, motion, and causality might be the illusion cast by a hidden, lower-dimensional layer. Reality could be encoded like a cosmic database, projected onto the stage where we live out our lives. Even though our actual universe isn't ADS, it's expanding, not curved inward. ADS remains one of the cleanest, most solvable models in physics. It's a lab where researchers can test the deepest questions of existence. What is space? What is time? What is information? What happens at the edge of a black hole? Can the universe itself be decoded? One of the most fascinating uses of ADS/CFT is in studying black holes. Normally, the inside of a black hole is a region of mystery. Beyond the event horizon, no signals can escape, and no information seems to return. But in the ADS model, every detail about what happens inside a black hole is somehow reflected on the boundary, in a holographic record that preserves every flicker of quantum data. It suggests a possible answer to the black hole information paradox, that nothing is truly lost, only translated, and it gets weirder. This theory connects with string theory, quantum gravity, and even the nature of consciousness. It suggests that space and time aren't fundamental building blocks of the universe at all, but emergent properties, created by the entanglement of quantum bits living on a lower-dimensional frontier. When you stare up at the night sky, you're looking out into what seems like an infinite expanse. But if anti-de Sitter space has taught us anything, it's that what we see might be a veil. A projection. A shadow. Somewhere beyond that veil, the true code of reality could be written, not in stars or galaxies, but in mathematical symmetries and the soft hum of quantum fields at the edge of existence. Mirror matter theory stands at the crossroads of quantum physics and cosmology, offering a bold, fascinating extension of our understanding of the universe. Imagine a parallel, hidden world composed of mirror particles, invisible to us, yet influencing everything around us. This theory suggests that for every particle in the universe, from electrons to quarks, there exists a corresponding mirror particle. These mirror particles would behave in exactly the same way as ordinary particles but would interact only with gravity, not with light or other forces we can detect. The origin of mirror matter theory lies in the discovery of symmetry in physics. While symmetry has long been an essential feature of many natural laws, there was a time when parity symmetry, essentially, the concept that the laws of physics should apply equally in both directions, was thought to be inviolable. However, experiments revealed that certain physical processes violate parity, particularly in the weak nuclear force. This shattered the assumption that parity symmetry was universally true. Mirror matter theory emerged as a speculative solution to this puzzle, proposing that symmetry is preserved, just in a hidden form. At the core of the theory is the idea that there's a mirror version of the universe. In this mirror universe, there are mirror particles that mirror the properties of particles in our own universe. For instance, where we have electrons, mirror matter would include mirror electrons. These mirror particles, however, don't interact with electromagnetic forces. As a result, we can't observe them using light, electricity, or any of the tools designed to study visible matter. This idea of invisible matter is tantalizing. It would explain why dark matter remains so elusive, even though we know it exists based on gravitational effects. Mirror matter could be the solution, because if mirror particles interact only through gravity, they would influence spacetime and objects in our universe without leaving any trace in the form of electromagnetic radiation or light. Essentially, these mirror particles would be undetectable by conventional means, yet they would still contribute to the overall mass of the universe, shaping galaxies and potentially affecting black holes and dark energy. The consequences of this theory reach beyond theoretical physics. Imagine a parallel world where mirror atoms and mirror stars exist. They would be gravitationally bound, yet invisible to our eyes and telescopes. Could such a world exist alongside our own? And could there be some kind of interaction between our universe and this hidden mirror world? The implications are mind-bending, as mirror matter theory suggests that the very fabric of reality could be far more complex than we previously imagined. One of the most compelling aspects of mirror matter is its ability to potentially explain certain cosmic phenomena that remain a mystery today. Take, for example, the Tunguska event in 1908, when a massive explosion flattened 2,000 square kilometers of forest in Siberia. The prevailing explanation has often been a comet or asteroid impact. However, some proponents of mirror matter theory suggest that the Tunguska explosion could have been caused by the collision of mirror matter with our universe, an event that would have released massive amounts of energy without any physical object appearing in our sky. The theory doesn't just deal with cosmic scale events, it also brings the possibility of mirror life. If mirror matter can form atoms and molecules just like ordinary matter, could mirror biology exist in parallel to ours? Life forms composed entirely of mirror particles might exist, their activities completely invisible to us, yet their gravitational influence felt. What could mirror organisms look like? How might mirror ecosystems function? The answers to these questions could radically transform our understanding of life, the universe, and everything within it. Another exciting potential application of mirror matter theory is the idea that mirror particles could be detected experimentally. One proposed method involves searching for neutron mirror-neutron oscillations, where neutrons spontaneously convert into mirror neutrons and vice versa. This phenomenon could potentially explain some of the mysterious behaviors of neutrons that scientists have observed in particle accelerators and in laboratory experiments. In conclusion, mirror matter theory does more than just challenge our understanding of particles, it redefines how we think about the universe. It introduces the possibility that the cosmos is far more intricate than we have ever imagined, with a hidden mirror world existing side by side with our own. And while the theory is still speculative, it offers a symmetrical solution to many of the problems that plague modern physics, from the nature of dark matter to the behavior of subatomic particles. If mirror matter exists, we may not just be living in one universe. We might be living in two, simultaneously. Conformal cyclic cosmology, CCC, proposed by the theoretical physicist Roger Penrose, challenges conventional ideas about the nature of time, the universe, and the fate of all existence. At its core, this theory presents a radically new vision of cosmology, one where the universe doesn't simply begin with the Big Bang and end in a distant, cold death. Instead, it suggests that the universe undergoes an eternal series of cycles, each beginning with its own Big Bang, and ending in a state where the end of time becomes the beginning of a new cycle. To understand CCC, we first need to address a crucial point: time and space, as we know them, are not fixed. In classical cosmology, the Big Bang marks the origin of time, and the eventual expansion of the universe leads to a predicted end, known as the Big Freeze or heat death. However, in conformal cyclic cosmology, Penrose proposes that time is not a straight, one-way path, but instead follows a cyclic, infinite series of eons, each one potentially stretching from one Big Bang to the next. The entire history of the universe is one of perpetual rebirth and renewal. The idea of CCC relies on a principle from conformal geometry, a branch of mathematics that deals with shapes that can be stretched, shrunk, or distorted without altering their basic structure. Penrose uses this concept to argue that the distinction between time and space disappears at extremely late times, particularly when the universe reaches a state dominated by the accelerated expansion of dark energy. As the universe continues to expand, the matter and energy inside it become diluted to the point where they are virtually indistinguishable. The fabric of spacetime itself becomes smooth and can be stretched to create a new Big Bang, which then begins a new cycle of the universe. The key insight of CCC is that the end of one universe becomes the beginning of the next. In this sense, the universe doesn't simply die in any traditional sense, rather, it smoothly transitions into a new phase of existence. The transition between the eons is governed by the concept of conformal invariance, which allows for the smooth stretching of spacetime without any loss of continuity. This process essentially means that the end of the universe in one cycle doesn't mark a true end. Instead, it is just another transition point toward the next cycle point. One of the most striking aspects of CCC is that it does not require the idea of a multiverse. The theory does not propose that our universe is just one of many. Instead, CCC suggests that all the eons are part of the same cosmic continuum. What we perceive as the beginning of time in our current universe, according to Penrose, is simply the latest Big Bang in an endless sequence of Big Bangs. This cyclic view of the cosmos also brings with it fascinating implications for the fate of black holes. In conventional cosmology, black holes are thought to eventually evaporate due to Hawking radiation, and their information would be lost forever. However, in CCC, Penrose suggests that the information contained in black holes is not destroyed. Instead, it is passed from one aeon to the next, preserving the essence of the previous universe in a way that allows for the continuity of cosmic evolution. The final state of the universe, dominated by black holes, leads to an infinitely smooth and empty space where the laws of physics as we know them cease to apply. Penrose's theory also offers a potential resolution to the fine-tuning problem, the question of why the constants of nature seem to be just right for life to exist. In CCC, the cosmological constants could be seen as remnants of the previous aeon, inherited and gradually evolving across cycles. The idea that the universe resets and evolves through many eons offers a long-term explanation for why the universe, at least from our perspective, is structured in a way that supports life. An important element of CCC is its connection to cosmic background radiation. Penrose proposed that, if the theory is correct, subtle imprints from the previous aeon might be observable in the cosmic microwave background, CMB, radiation of our current universe. He hypothesized that certain features, such as anomalous cold spots in the CMB, could be the remnants of black holes that were formed in the previous universe. If such imprints exist, they would provide an extraordinary glimpse into the previous cycle of the universe. The notion of eternal recurrence is one of the more poetic aspects of CCC. The idea that the universe is reborn again and again, infinitely cycling through big bangs and big crunches, mirrors ancient philosophical ideas about time and existence. From a cosmological perspective, it paints a picture of a universe that is not bound by linear time but instead exists in an eternal, cyclical flow, a notion that resonates with some ideas found in Eastern philosophy, particularly Buddhism and Hinduism, where the cosmos is seen as undergoing infinite cycles of creation, preservation, and destruction. While CCC is still a speculative theory and remains controversial in some scientific circles, it has sparked intriguing discussions about the true nature of time, space, and the universe. Its implications are vast, offering new perspectives on the fate of the cosmos, the role of dark energy, and the continuity of life across eons. The idea that we might live in an infinite cycle of cosmic rebirth invites us to think beyond the confines of our short-lived universe and imagine a reality far grander and more interconnected than we can perceive. Planck Star. The concept of the Planck Star delves deeply into the intersection of quantum mechanics and general relativity, offering a bold new perspective on one of the most mysterious objects in the universe, the black hole. The Planck Star hypothesis challenges the classical understanding of black holes, proposing that the event horizon does not lead to a singularity, as commonly thought, but to a unique quantum state of matter and energy. Traditionally, black holes are thought to collapse under their own gravity into a singularity, a point of infinite density where the laws of physics break down. Once something crosses the event horizon of a black hole, it is thought to be lost forever. This includes light, matter, and, most importantly, information. This led to the black hole information paradox, a problem in theoretical physics where information about particles that fall into a black hole seems to be destroyed, which conflicts with quantum mechanics, where the principle of information conservation is fundamental. The idea of the Planck star arises from the attempt to reconcile this paradox with the principles of quantum gravity, an area of physics that seeks to unify quantum mechanics with general relativity. It posits that as matter collapses into a black hole, it doesn't actually collapse into an infinite singularity. Instead, it undergoes a dramatic transformation, reaching a point where the effects of quantum mechanics dominate. At the heart of the Planck star concept is the idea of a quantum bounce. Instead of continuing to collapse indefinitely, the matter within a black hole reaches a point of extreme density and then bounces back, avoiding the formation of a singularity. This bounce could occur at a size on the order of the Planck length, the smallest length scale in physics, roughly 10 to the power of -35 meters, where quantum gravitational effects become significant. This suggests that black holes might not destroy information, but rather transform it. The matter and energy within a Planck star could, in theory, be released back into the universe in a modified form. The event horizon would no longer mark the point of no return. Instead, it would be part of a dynamic process where matter and energy undergo transformation rather than destruction. The Planck star also presents an intriguing potential solution to the black hole information paradox. If black holes are indeed able to undergo a quantum bounce, this would imply that the information swallowed by the black hole could eventually escape, in a form radically altered by the quantum processes occurring inside. This might allow for the preservation of information, thereby maintaining consistency with quantum theory, which dictates that information cannot be destroyed. The implications of the Planck star theory stretch far beyond black holes. If the bounce mechanism holds true, it could fundamentally alter our understanding of space, time, and gravity. It suggests a universe where the boundaries between different states of matter and energy are not as rigid as we once thought. Rather than a one-way collapse into a singularity, the universe might operate on cycles of transformation, with matter constantly undergoing quantum-level changes. This theory also brings into question our understanding of time. In the classical view, time as we know it ceases to exist inside a black hole, where the laws of physics break down. However, if Planck stars exist, they could introduce a new model where time is still meaningful inside a black hole, albeit in a radically different way. The matter and energy inside the Planck star may be frozen in time, but this frozen state is not the end. Instead, it could be part of a cyclical process of transformation. The Planck star hypothesis is still a work in progress in theoretical physics, and there are many unanswered questions surrounding it. However, it represents an exciting and innovative step toward understanding the most enigmatic objects in the universe. If proven true, the Planck star theory could pave the way for a new era of physics, where the mysteries of black holes, quantum gravity, and the nature of space-time itself are revealed in ways we have only begun to imagine. Vacuum tunneling, or quantum tunneling, is a fascinating phenomenon that occurs at the subatomic level, where particles bypass energy barriers they seemingly shouldn't be able to overcome according to classical physics. This concept lies at the heart of quantum mechanics, a field that explores the strange and counterintuitive behaviors of particles at the smallest scales. The idea of tunneling goes against our everyday intuition, but it plays a crucial role in many physical processes, both theoretical and observed. In classical physics, if a particle doesn't have enough energy to overcome a barrier, say, a hill, it would simply be unable to cross it. However, quantum mechanics allows for a different reality. Instead of being confined to the regions where it has sufficient energy, a particle has a probability of appearing on the other side of the barrier, even if it doesn't have enough energy to climb over it. This process is known as quantum tunneling. The most well-known example of tunneling is alpha decay, a type of radioactive decay. In alpha decay, a nucleus emits an alpha particle, essentially a helium nucleus, and, classically, the alpha particle doesn't have enough energy to overcome the potential barrier surrounding the nucleus. Yet, quantum mechanics allows the alpha particle to tunnel through this barrier, escaping from the nucleus and causing the radioactive decay. Vacuum tunneling is a special case of this phenomenon that happens on a much grander scale. It involves the vacuum of space itself, which in quantum theory is not empty but filled with fluctuating energy fields. These fluctuations create a false vacuum, a temporary state of lower energy than the true vacuum of the universe, which is thought to be the most stable state possible. Essentially, the false vacuum is a region of space where the laws of physics are not in their lowest energy, most stable configuration. Vacuum tunneling in this context suggests that it is possible for the universe to tunnel from one state to another, from a false vacuum to a true vacuum. If such a tunneling event were to occur, it would have enormous consequences. The transition from the false vacuum to the true vacuum would release an immense amount of energy, likely in the form of a bubble of true vacuum expanding at the speed of light. This bubble would sweep through the universe, fundamentally altering the laws of physics within it, potentially destroying everything it encounters. Such a process, though purely theoretical, could have cataclysmic implications for the entire cosmos. One of the most profound implications of vacuum tunneling is its potential connection to the origin of the universe itself. According to some models of cosmic inflation, the universe began in a state of false vacuum and then underwent a transition to a true vacuum state, sparking the rapid expansion that led to the formation of the universe we observe today. This idea links vacuum tunneling directly to the Big Bang theory, offering a possible mechanism for the creation of the universe from a quantum fluctuation. But vacuum tunneling is not just a theoretical curiosity. It has real-world implications in fields such as cosmology, particle physics, and even technology. For example, tunneling is a critical process in quantum computing, where particles can tunnel through energy barriers to perform calculations far faster than traditional computers. The ability to harness tunneling on a microscopic scale has the potential to revolutionize computing, leading to exponentially more powerful machines. In the context of cosmology, vacuum tunneling has prompted a deeper investigation into the nature of the universe's vacuum state, the underlying energy field that gives rise to all matter and forces. The possibility that our universe could transition into another, completely different state challenges our understanding of the universe's stability and raises profound questions about the ultimate fate of everything we know. The theory of vacuum tunneling also suggests that our universe may not be the only one out there. In fact, it implies that multiple universes, or multiverses, could exist, each with different vacuum states and physical laws. If vacuum tunneling can occur between different regions of the universe or across different universes, it opens the door to an infinite array of potential realities, each with its own unique configuration of matter, energy, and physical laws. This idea is both mind-boggling and exciting, hinting at the possibility of an infinite number of universes, each created by its own quantum tunneling event. While the concept of vacuum tunneling remains theoretical, it offers an exciting way to understand some of the most fundamental processes in the universe. Whether it's explaining the birth of the cosmos, offering new insights into quantum mechanics, or even shaping the future of technology. Vacuum tunneling provides a glimpse into the strange and profound nature of reality itself. As scientists continue to study this phenomenon, it may one day help us uncover the deepest secrets of the universe, offering answers to questions that have remained hidden for centuries. Cueballs. Cueballs are an incredibly intriguing and theoretical concept in the world of particle physics. At the core of this idea is the idea of non-topological solitons, which are stable, localized configurations of a scalar field that are held together by forces that don't rely on topological charges like those seen in traditional solitons. A soliton is a type of wave-like solution that maintains its shape over time, but unlike regular waves, a soliton does not lose energy or decay, it persists. In the case of cueballs, these solitons have some fascinating and somewhat eerie properties that could shed light on a variety of profound questions about the universe, particularly in the realms of dark matter and theoretical particle physics. Cueballs are named after the charge parameter, Q, that distinguishes them from other types of solitons. These objects arise in theories that involve scalar fields, fields that assign a value to every point in space, and whose energy is described by a scalar, as opposed to vector fields where energy can be described by multiple components. Scalar fields are central to many aspects of particle physics, including theories like supersymmetry and string theory. Cueballs come into play when a certain type of scalar field exhibits self-interaction, meaning that the field interacts with itself, causing it to form stable configurations that don't disperse. What makes cueballs particularly interesting is that they can potentially store large amounts of energy and have a very long lifetime. Their formation requires a particular kind of symmetry, and these solitons are stable even in the absence of any topological charge. This characteristic sets them apart from many other kinds of solitons, which rely on certain kinds of symmetry to maintain their stability. The fact that cueballs do not require topological charge for their stability makes them especially mysterious and exciting in the context of modern physics. The formation of cueballs depends on the symmetry breaking in a field theory. In simpler terms, when the symmetry of a system is broken, new states of matter can emerge, and these new states may possess unique properties that are not present in the underlying symmetric state. For cueballs to form, a symmetry breaking mechanism must be at play, resulting in a field configuration that becomes stable enough to persist for long periods of time, even potentially indefinitely. Cueballs have the potential to explain certain phenomena in the cosmos. One of the most compelling ideas is their connection to dark matter. Dark matter, which makes up about 27% of the universe's mass, has been one of the biggest mysteries in astrophysics. While we know dark matter exists because of its gravitational effects on visible matter, it doesn't interact with light or other forms of electromagnetic radiation, which makes it invisible. Cueballs, with their ability to interact with other particles via scalar fields, could be one possible candidate for dark matter. These stable, non-topological objects might be able to explain why dark matter doesn't show up in traditional particle detectors. It may not be composed of standard particles at all, but instead be made up of these elusive solitons. Cueballs might also help to answer questions about the early universe. In certain models of the early cosmos, scalar fields could have played a crucial role in the formation of the universe we know today. Cueballs could have formed in the dense conditions of the early universe, acting as a kind of cosmic seed, with their presence potentially influencing the evolution of the cosmos. Because cueballs can remain stable for incredibly long periods, they might offer a mechanism by which certain phenomena in cosmology could be preserved across vast stretches of time, serving as relics from the very birth of the universe. The theoretical framework behind cueballs also touches on supersymmetry and string theory, both of which suggest the existence of new kinds of particles and fields that extend beyond the standard model of particle physics. Supersymmetry, for instance, predicts that every particle has a superpartner, and scalar fields like those responsible for cueballs might be connected to these supersymmetric particles. If cueballs exist, they could be linked to these elusive superpartners, offering a new way to explore the frontiers of physics. although cueballs have not been observed directly, their theoretical implications are vast and could offer insights into some of the most profound questions about the nature of matter, energy, and the universe. Their potential connection to dark matter, the early universe, and beyond the standard model physics makes them an exciting area of exploration for future research. In summary, cueballs are theoretical, stable, non-topological solitons formed by scalar fields with self-interactions. These enigmatic entities could potentially serve as a candidate for dark matter, provide answers about the early universe, and challenge our understanding of particle physics. Despite their elusive nature, cueballs represent one of the many fascinating possibilities that quantum field theories and cosmological models bring to the table, and as such, they stand as one of the many intriguing phenomena that await further investigation in the quest to understand the deepest truths of the universe. Emergent gravity. Emergent gravity represents a groundbreaking shift in our understanding of one of the most fundamental forces in the universe, gravity. Unlike traditional views where gravity is treated as a basic interaction akin to electromagnetism or the strong nuclear force, emergent gravity proposes that gravity itself is not a fundamental force. Instead, it is a result of deeper microscopic interactions within the fabric of spacetime, emerging as an effect from the collective behavior of quantum degrees of freedom. The concept was largely brought into the spotlight by theoretical physicist Eric Verland, who in the early 2010s put forward the idea that gravity is not a fundamental force, but an entropic force, a force that arises from the statistical behavior of microscopic degrees of freedom. Entropic forces are not fundamental forces in the traditional sense, but are instead the result of the arrangement of information or microscopic states that exist in a system. In Verland's theory, gravity emerges from the thermodynamic properties of spacetime, much like other macroscopic phenomena arise from the collective behavior of atoms or molecules. Verland's proposal builds on the holographic principle, a concept from theoretical physics that suggests that all the information contained within a region of space can be encoded on the boundary of that region. This principle, often associated with string theory, suggests that our three-dimensional reality might be a projection from two-dimensional information encoded at the boundary of space. According to Verland, gravity arises from the information flow and the microscopic interactions at the boundaries of space, essentially linking the forces of gravity to the behavior of quantum information. A crucial aspect of emergent gravity is its potential to explain phenomena traditionally attributed to dark matter. For instance, in galaxy clusters, galaxies rotate faster than can be accounted for by the visible matter alone, leading scientists to propose the existence of dark matter, a mysterious substance that doesn't emit light but exerts gravitational influence. However, emergent gravity suggests that the observed gravitational anomalies may not require dark matter at all. Instead, these effects could simply arise from the behavior of spacetime itself at large scales, where gravity behaves in unexpected ways due to the emergent properties of spacetime. Moreover, this approach offers intriguing insights into unresolved issues in modern physics, such as the black hole information paradox. According to conventional wisdom, when matter falls into a black hole, it seemingly disappears from the observable universe, and the information about that matter is lost. However, in the emergent gravity framework, this loss of information could be an illusion. The information about the matter may still exist, encoded in the quantum states of spacetime itself. This idea could potentially provide a resolution to the long-standing debate about whether or not information is truly lost in black holes. Emergent gravity also offers a fresh perspective on the relationship between quantum mechanics and general relativity, two of the most successful yet incompatible theories in modern physics. While general relativity describes the gravitational force at large scales, quantum mechanics explains the behavior of particles at microscopic scales. By proposing that gravity is an emergent phenomenon arising from quantum information, Verland's theory provides a possible bridge between these two domains, bringing us closer to a unified theory of quantum gravity. Despite its innovative nature, emergent gravity remains a speculative idea and has not yet been proven experimentally. Critics of the theory argue that it does not yet provide concrete experimental predictions or explanations that could definitively support it over traditional models of gravity. Nonetheless, emergent gravity presents a radical departure from established views and opens up new avenues for exploring fundamental questions about dark matter, the nature of gravity, and the very structure of spacetime. If experimental evidence were to support the theory, it could revolutionize our understanding of the universe, offering profound insights into how the cosmos functions at its most basic level. Axiverse. The Axiverse is a fascinating and highly speculative concept in modern theoretical physics that stems from the study of axions, a hypothetical elementary particle. This idea is not just about the axion itself, but about a potential vast universe of axions, where many different axions exist, each with its own characteristics and properties, contributing to a broader cosmological picture that could offer solutions to some of the most profound mysteries of the universe. At its core, the axion is a theoretical particle that was first proposed in the 1970s by theoretical physicists Roberta Pecchiai and Helen Quinn to address a problem in the standard model of particle physics, known as the strong CP problem. This problem arose because the strong nuclear force, which binds quarks together inside protons and neutrons, should theoretically violate CP symmetry, the symmetry between particles and antiparticles, but no such violation has been observed. The introduction of the axion was one way to solve this puzzle. Axions, if they exist, would be very light, electrically neutral, and interact only weakly with matter, which makes them incredibly difficult to detect directly, but the story of the axion doesn't stop there. In recent years, the idea of the Axiverse has emerged, suggesting that there is not just one axion, but rather an entire multiverse of axions with different masses and coupling constants. This array of axions could have significant implications for both particle physics and cosmology. The concept is deeply connected to theories of string theory and the cosmic landscape, where the fundamental properties of the universe, such as the types of particles and forces that exist, could arise from different configurations of extra dimensions and string vibrations. Within this framework, axions could be the result of different vibrational modes of strings, each mode corresponding to a different axion in the Axiverse. One of the most compelling aspects of the Axiverse is its potential connection to dark matter. Dark matter is an elusive substance that is thought to make up about 85% of the mass of the universe, but it does not emit, absorb, or reflect light, making it invisible to telescopes. Its existence is inferred from its gravitational effects on visible matter, such as the rotation curves of galaxies and the behavior of galaxy clusters. The Axiverse could provide a novel explanation for dark matter, with the various axions acting as possible dark matter candidates. In this context, the Axiverse offers an intriguing possibility that axions might be the particles that make up dark matter, contributing to the gravitational effects observed in the cosmos. Moreover, the Axiverse could help explain some of the most perplexing observations in cosmology, such as the cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, and its precise measurement provides crucial insights into the early universe. Axions from the Axiverse could have played a role in the formation of the CMB, potentially explaining some of the anomalies observed in the radiation spectrum. The Axiverse also has ties to the search for cosmic inflation, the rapid expansion of the universe that is believed to have occurred in the first fraction of a second after the Big Bang. Many string theory-based models suggest that axions might have influenced the inflationary process, contributing to the dynamics that shaped the evolution of the universe at its earliest stages. In this view, the Axiverse may provide a key piece in the puzzle of how the universe expanded and evolved from a singularity to the vast cosmos we observe today. Despite the promise of the Axiverse, it remains a highly speculative concept. Axions themselves have not yet been detected, and the idea of the Axiverse, with its multitude of axions, is still very much in the realm of theoretical physics. However, there are ongoing experimental efforts aimed at detecting axions, including sensitive experiments that search for the faintest signals that would indicate the presence of these particles. One such effort is the Casper experiment, which aims to detect axions by measuring their effects on nuclear spins. If axions are indeed discovered, they could revolutionize our understanding of the universe, opening new doors to both fundamental particle physics and cosmology. Dark photon. The dark photon is a hypothetical particle that could provide a key link between the visible and invisible components of the universe. In simple terms, it is a theoretical cousin of the photon, the particle that mediates the electromagnetic force in our universe. While the photon is the carrier of light and other electromagnetic interactions, the dark photon is postulated to mediate interactions in the dark sector, a mysterious and largely unexplored part of the universe. This idea is rooted in the broader search for a better understanding of dark matter and its elusive properties. The concept of dark photons arises from the notion that there may exist a hidden sector of particles and forces that are distinct from the particles and forces of the standard model of particle physics. The standard model includes familiar particles like electrons, quarks, and neutrinos, which interact with each other through the four known fundamental forces: gravity, electromagnetism, the weak force, and the strong force. However, the vast majority of the universe's mass is made up of something that does not interact via these forces: dark matter. This invisible substance, which has been inferred through its gravitational effects on visible matter, remains one of the greatest mysteries in modern physics. In order to understand dark matter, physicists have postulated the existence of a dark sector, which may involve its own particles and forces. The dark photon is one such particle, proposed as the force carrier for interactions within this hidden sector. The hypothesis is that dark photons could interact with dark matter particles in ways similar to how ordinary photons interact with regular matter, except that the dark photon would not interact with the ordinary particles of the standard model, or it would interact very weakly. Dark photons are typically thought to be very similar to regular photons in that they mediate a force, but with one key difference. Dark photons could have a small mass or a very weak interaction with regular matter. This small mass could make dark photons difficult to detect, as they would not travel at the speed of light, unlike regular photons. The existence of such particles would help explain some of the strange behaviors observed in the universe, including phenomena related to dark matter and dark energy. One intriguing possibility is that dark photons could be coupled to ordinary photons through a process known as kinetic mixing. Kinetic mixing would allow dark photons to interact weakly with regular photons, creating a small overlap between the visible sector and the dark sector. This interaction could manifest in detectable ways, such as the production of dark photons in high-energy experiments, or through the effects they would have on the cosmic microwave background (CMB) radiation. Essentially, dark photons might be able to leak into our visible universe, leaving subtle imprints on the observable effects we see in space. The search for dark photons is a significant part of the hunt for dark matter and the exploration of the dark sector. Several experiments are actively investigating the possibility that dark photons could be detected indirectly through their effects on the behavior of ordinary particles or by observing anomalies in the way light interacts with matter. For example, dark photons could be produced in particle accelerators or high-energy experiments, and their decay products might be observed as unusual signatures in detectors. Additionally, astrophysical observations, such as those of galaxy clusters or cosmic rays, could potentially reveal the influence of dark photons on the behavior of dark matter. One of the most intriguing potential consequences of dark photons is their role in explaining some of the unexplained anomalies in astrophysics and cosmology. For example, the discrepancy between the amount of visible matter and the effects of gravitational forces in galaxies and galaxy clusters could be linked to interactions involving dark photons. These interactions could potentially explain some of the missing mass in the universe that is attributed to dark matter. Dark photons might also help solve some long-standing puzzles about dark energy, which is thought to account for the accelerated expansion of the universe. In this context, dark photons could provide a mechanism through which dark energy interacts with matter, offering a potential solution to the mystery of the universe's accelerated expansion. Despite its potential, the dark photon remains a highly speculative concept. While it is theoretically consistent with known physics, and provides a possible link between dark matter and the electromagnetic force, no experimental evidence yet exists for its existence. The challenge of detecting dark photons is immense, given that they interact only weakly with normal matter, making them exceedingly difficult to observe directly. Nevertheless, experiments such as the Dark Photon Search at the Fermilab and the ALPS-2 experiment in Europe are pushing the boundaries of what we can detect and measure, with the hope that one day, dark photons will be found. Quantum hair on black holes, one of the most mysterious objects in the universe, are typically described by three properties: mass, charge, and angular momentum. However, the idea of quantum hair challenges this conventional view. Quantum hair suggests that black holes might possess quantum states beyond these three classical properties, potentially offering a solution to the black hole information paradox. Traditionally, the no-hair theorem in general relativity held that once a black hole reaches equilibrium, all the information about the matter that formed it or fell into it is lost, leaving only these three observable properties. However, quantum mechanics introduces a wrinkle to this idea, where information about quantum systems is never truly lost. The notion of quantum hair proposes that black holes could store additional quantum information, possibly in the form of exotic quantum states located at the event horizon, thus preserving information about the matter that fell into the black hole. This concept is a potential resolution to the black hole information paradox, which arises because, according to classical physics, information that crosses a black hole's event horizon is lost. In quantum mechanics, however, information is conserved. The hypothesis of quantum hair suggests that this information may not be lost, but instead encoded in quantum states at the black hole's surface, offering a potential mechanism by which the information could be recovered. The quantum hair could be associated with the behavior of the event horizon itself, where the quantum states would carry the data of everything that entered the black hole. This might allow the black hole to maintain a form of memory about its past. One of the implications of quantum hair is that it could lead to changes in the way we understand Hawking radiation, a quantum process by which black holes could potentially emit radiation, possibly shedding light on the missing information. Additionally, quantum hair could impact black hole thermodynamics. According to the Bekenstein-Hawking entropy, black holes have an entropy proportional to the area of their event horizon. If quantum hair exists, it could increase the amount of entropy associated with the black hole, possibly reshaping our understanding of the thermodynamic properties of black holes. Detecting quantum hair is challenging, but it might leave subtle clues in phenomena like gravitational wave signals from black hole mergers or in the behavior of Hawking radiation. The idea could also offer valuable insights into quantum gravity, which seeks to unite quantum mechanics and general relativity. If quantum hair is real, it might provide a crucial clue for understanding the quantum structure of spacetime, particularly at the event horizon. In summary, the concept of quantum hair challenges the traditional view of black holes as featureless objects, suggesting they may hold a deeper quantum structure that encodes information about their past. This theory has profound implications for our understanding of black holes, quantum mechanics, and the nature of reality itself. Time reversal symmetry violation. In physics, symmetry refers to the invariance of a system under certain transformations. One of the most fundamental symmetries in the laws of physics is time reversal symmetry, which implies that the equations governing physical phenomena should remain unchanged if time were to be reversed. This symmetry suggests that the fundamental laws of nature should behave in the same way whether time moves forward or backward. However, the idea of time reversal symmetry violation proposes that, under certain conditions, time may not be completely symmetric. In other words, certain physical processes could behave differently when time is reversed, indicating an asymmetry in the way time flows. This concept challenges our traditional view of the universe and has significant implications for understanding the underlying workings of nature, particularly in the realms of particle physics and cosmology. One of the most famous examples of time reversal symmetry violation arises in the study of weak interactions, one of the four fundamental forces of nature. The weak force, which is responsible for processes like beta decay in nuclear physics, has been shown to violate time-reversal symmetry in certain instances. This violation was first observed in the 1950s during experiments involving the decays of kaons, particles containing strange quarks. In these experiments, it was found that the decay of kaons did not behave symmetrically under time reversal, as the process seemed to prefer one direction of time over the other. This violation is not just an academic curiosity, but it has real-world implications. For example, the violation of time reversal symmetry is closely tied to the phenomenon of CP violation, where C stands for charge conjugation symmetry and P stands for parity symmetry. CP violation, which is observed in certain particle decays, is essential for understanding why the universe appears to be dominated by matter rather than antimatter. In the early universe, matter and antimatter were created in equal amounts, but through processes that violated both time reversal and charge parity symmetry, an excess of matter over antimatter was created, leading to the universe we observe today. The study of time reversal symmetry violation also has potential connections to the search for a unified theory of physics. It is often discussed in the context of quantum mechanics and quantum field theory, where the behavior of particles at subatomic scales can sometimes defy classical expectations. The violation of time reversal symmetry in weak interactions is part of a broader effort to understand how the different forces of nature, particularly gravity, electromagnetic force, and the weak and strong nuclear forces, can be unified under a single framework. On a more speculative level, time reversal symmetry violation could also have cosmological implications. Some theories of the Big Bang suggest that the early universe may have undergone processes that were not symmetric in time, and the violation of time reversal symmetry might be a key factor in the arrow of time, the one-way flow of time that we experience. Understanding how time behaves at quantum scales and whether there are deeper mechanisms that violate this symmetry could open up new insights into the origins of the universe and the nature of time itself. In summary, time reversal symmetry violation is a fascinating concept that challenges our classical understanding of time and the laws of nature. Observed in weak interactions and related phenomena like CP violation, this asymmetry has profound implications for particle physics, the origins of matter, and our understanding of the universe at its most fundamental level. While much is still to be explored, time reversal symmetry violation could be key to unlocking some of the deepest mysteries of the cosmos. Topological defects in the early universe. Topological defects are fascinating and profound features that arose during the very early stages of the universe, providing essential clues about its fundamental nature. These defects are tied to the concept of topology, which deals with the properties of space that remain invariant under continuous transformations. In cosmology, topological defects are defects in the structure of space-time that form during phase transitions in the early universe when the temperature and energy levels were extremely high. These transitions, driven by the cooling of the universe, broke certain symmetries in the fundamental fields of physics and led to the emergence of these unusual structures. Topological defects are important because they reflect the way space itself behaves under extreme conditions and how the universe's fundamental forces took shape during the first moments after the Big Bang. There are three primary categories of these defects that are theorized to have emerged during the early universe's cooling process. Domain walls. These are two-dimensional defects that represent boundaries between regions of space where the field has different values. Imagine a transition between two distinct phases, like the boundary between water and ice, only in this case, the boundary is between different phases of the field's vacuum state. Domain walls are expected to have formed when the field's symmetry broke and different regions of the universe adopted different vacuum states. While domain walls might have been crucial during the formation of cosmic structures, their potential existence poses questions about the future evolution of the universe. If they exist today, domain walls would likely exert some influence on the current expansion of the universe and the distribution of matter, but they would also be highly unstable, potentially decaying over time. Cosmic strings. These one-dimensional, infinitely long, and incredibly dense structures are thought to have emerged as a consequence of symmetry-breaking events in the early universe. cosmic strings could theoretically stretch across the universe, impacting the distribution of galaxies and large-scale structures. Their existence could have profound implications on how we understand the universe's formation. These defects are potentially detectable through their gravitational effects, as the immense density of cosmic strings would warp the fabric of spacetime. The detection of gravitational waves caused by cosmic strings would represent a significant breakthrough in observational cosmology and could provide a direct link to the universe's early stages. Monopoles. A third type of topological defect is the magnetic monopole, which is a point-like defect carrying a single magnetic charge. In contrast to ordinary magnetic dipoles, which have both a north and south pole, monopoles would have only one pole. They are predicted to have emerged during the early universe's cooling and symmetry breaking processes. Although magnetic monopoles have not yet been observed experimentally, their potential existence remains a key theoretical aspect of high-energy physics. If they were to be found, it would provide an essential piece of the puzzle, offering insight into the unification of the fundamental forces of nature and the conditions that prevailed during the first moments of the universe. Topological defects are intimately connected with symmetry-breaking events, particularly the electroweak symmetry breaking that occurred in the first fraction of a second after the Big Bang. During this phase transition, the electromagnetic and weak nuclear forces, which were unified in a single force, separated, causing a cascade of effects that led to the formation of distinct vacuum states across different regions of space. These symmetry-breaking events were analogous to the crystallization process in materials, where certain patterns emerge as the system cools and transitions between different phases. What makes the study of topological defects particularly exciting is their potential to explain certain mysteries of the universe. For example, cosmic strings, if they exist, could be responsible for shaping the distribution of galaxies and large-scale structures within the universe. Furthermore, they could generate gravitational waves, providing a unique opportunity to detect them with current observatories. Similarly, domain walls could be linked to the phenomenon of dark energy, which is driving the accelerated expansion of the universe. Their effects on the evolution of the universe would be profound, potentially shaping not only its structure but also its long-term fate. In addition to providing clues about the forces that shape the universe, topological defects also give us insight into the nature of spacetime itself. If these defects are real, they would serve as windows into the earliest moments of the cosmos, revealing the dynamics and interactions of fundamental fields. By studying them, scientists can better understand the processes that took place in the infancy of the universe, the fundamental laws of physics, and how the universe evolved from a hot, dense state to the vast, complex structure we see today. Black hole lasers. Black holes are often seen as objects of destruction, capable of devouring anything, including light, that crosses their event horizon. However, an intriguing concept in theoretical physics proposes that black holes might produce something akin to a laser, a coherent beam of radiation. This idea, though counterintuitive, emerges from understanding the extreme quantum environment surrounding black holes. A laser typically works by emitting coherent light or radiation through a process called stimulated emission, where particles in an excited state are stimulated to release photons in a synchronized manner. In the case of black holes, the environment near the event horizon could, theoretically, create a similar effect, except that instead of light, it could involve other forms of electromagnetic radiation, such as X-rays or gamma rays. This concept has its roots in the theoretical work of Stephen Hawking, particularly his prediction of Hawking radiation. According to Hawking's theory, black holes aren't completely black. Instead, they emit radiation due to quantum fluctuations at the event horizon. These fluctuations create pairs of particles, one of which escapes the black hole, while the other falls in. The escaping particle results in what we observe as radiation coming from the black hole. While this radiation is typically weak and diffuse, under the right conditions, it could become coherent. Black hole lasers would require a high-energy environment, such as an accretion disk, a swirling mass of gas and dust spiraling into the black hole. If the radiation from the accretion disk were to interact with the black hole's intense gravitational and magnetic fields, it could potentially become amplified and focused, much like the light produced by a traditional laser. One model for how black hole lasers could work involves the interaction between the accretion disk and the black hole's magnetic field. As material in the accretion disk heats up and emits radiation, the black hole's powerful magnetic fields could focus and direct this radiation. If the conditions are right, this could create a beam of coherent radiation, akin to a laser. While no evidence yet supports the existence of black hole lasers, the idea is a fascinating extension of our understanding of black holes and quantum mechanics. If proven true, it would offer new insights into the extreme environments around black holes and open up new avenues of study in astrophysics and quantum physics. In conclusion, black hole lasers represent a theoretical phenomenon in which black holes could emit coherent beams of radiation, challenging our conventional understanding of these objects. Though speculative, the idea pushes the boundaries of our knowledge about the interaction of matter, energy, and gravity in some of the most extreme environments in the universe. Whether or not these lasers exist in reality, the concept presents an exciting area for future research in astrophysics.